In this video, I'm going to show the image of why we need the impedance matching with coils, especially T-coil. Here is the image of a differential signal SerDes system. Could you guess if there's any impairment around the interface with the red circle? Think about your impedance images for 5 seconds. Right, reflection. We've briefly discussed the reflection in the white noise video. As you can tell, with an impedance mismatch, the resistive signal power is less, and that would degrade the SNR signal-to-noise ratio because of the distorted signal power. To improve the link performance of the receiver input sensitivity, what can we do to reduce the reflection? Think about your matching images for 5 seconds. Correct. If the impedance mismatch introduces the reflection, why don't we just make the impedance match at the interface? Therefore, adding the resistive termination would achieve the impedance match at the interface between the SerDes and the channel. Improving the impedance match will certainly reduce the reflection. But how do we know if the added resistive termination is good enough? Fortunately, the MOS standard will specify the return loss specification to make sure a compatible link, and that will provide a guideline for the electronics ecosystem supply chain. Let's take the return loss specification from the OIF CI. For example, the differential return loss must be less than -8 dB at 100 MHz. Therefore, the resistive mismatch could have a substantial amount of tolerance. Just give you an idea of the 100 ohm differential impedance as the return loss case study here. The termination impedance could be as low as 50 ohm or up to 200 ohm without violating the specification at DC, around 100 MHz. But what caused the return loss violation at high frequency? Correct. Big I/O capacitance caused the high frequency return loss issue. In Electronics 101, you may know the impedance of the capacitance is inversely proportional to the frequency and capacitance. In other words, the capacitive impedance might not be an issue in the past for 1 gigabit per second SerDes, but it would be an issue for 10 gigabit per second or higher data rates, since the impedance is 10x less if the same I/O impedance capacitance there. Therefore, the bigger capacitance will lead to a smaller impedance at a fixed frequency. Let's go through a case study at 10 gigabit per second, which is a high data rate demand nowadays. By sweeping the capacitance at the I/O, we can see the return loss at 10 GHz violate the -8 dB specification if the capacitance is larger than 400 femtofarad. But unfortunately, the ESD may be required to meet a 2 kV human body model or above, which may lead to a big capacitance at the I/O. In addition, the bonding pad or bump is needed for the package, and the metal capacitance could be big. Lastly, the circuit itself that the TX driver is big to drive the 50 ohm load and achieve a big swing up to 800 mV peak-to-peak differential. So both the device and passive capacitance will be big on chip. What can we do? Bingo! Adding the coils will help. Those added capacitance must be mitigated with the coils to shift the total impedance higher to a higher frequency. A case study without any coil may show you the return loss would be improved from 650 femtofarad to 450 femtofarad, but still not meet the specification because the limit impedance match improvement. Fortunately, by adding the coil for the 450 femtofarad capacitive load, the return loss can meet the specification of minus 8 dB at 10 GHz and minus 6 dB up to 12 GHz. Is this single inductor coil good enough? If not, what else we could do? For a lossless transmission line at high frequencies greater than 100 MHz, the transmission line trace is a distributed model with a constant characteristic impedance Z0 around 100 ohm in the differential. As you can see, the simplified transmission line is an LC-LC. Multiple LC ladder in a cascaded that could achieve a wide bandwidth or constant impedance over frequencies. Would this imagery help you to come up with another broadband coil imagery? Bingo! Add more coils to mimic the multiple LC ladder to achieve a wide bandwidth or constant impedance over frequencies. The added coil was called T-Coil because of its shape, which makes more broadband matching than the single inductor coil. As you can see from the case study here, without any coil in the red curve, the return loss will violate the specification as we discussed. With a single inductor matching in the yellow curve, we could meet the return loss specification with little margin. By applying the T-coil in the design, as you can see in the green curve, the return loss would be better at high frequency and have more margin for higher data rate application. Besides the return loss, what else we can benefit from the T-coil matching? Correct. The front-end bandwidth would be extended. Therefore, the signal's transition time can be reduced, or the deterministic jitter of the eye can be reduced a lot. If we compare the transition time in both cases, the T-coil design can improve the transition time by 30% more than the single inductor case. But there's a little subtlety in the eye diagram. Could you notice it and make a guess? Yes, the ringing may happen with more coils, and we need to make sure the ringing will be settled down within one bit period, such that no intersymbol interference occurs. Again, this green eye is still fine, since the ringing settled down quickly within one bit period. Here is a summarized image you may have for why you need a T-coil impedance matching in a high-speed SerDes system. The goal is to maintain the signal integrity to reduce the bit error rate. The signal integrity could be improved by adding impedance matching property, which will increase the signal-to-noise ratio SNR. For example, the reflective signal would be minimized, or the incident signal level would be maximized from DC to data rate frequency. In addition, good matching will extend the signal bandwidth to boost the transition time of the signal and reduce the deterministic jitter property. In this wide impedance matching video, the T-coil was demonstrated to achieve the impedance matching effectively, not only for the return loss, but also as a big eye-opening. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may be benefiting from it.